Look how that
I think you said the week after next week, not as actual date.
Okay, let me just take a look quickly at my planner. Yes, it's actually next week. Okay, so I'm going to need declarations from you to say that you did not cheat. You can pick your day. When would you like a test? Do you want it on the Thursday again? Get it over and
Sorry,
done
ma'am,
with.
please repeat the question.
Would you like your test next week? You have a test next week. Would you like it on, what day would you like it? Do you want it on the Thursday?
Maybe Tuesday?
Tuesday? Would you guys want to take the week and maybe I can help you on the Monday, Tuesday, Wednesday? And you finish off on the Thursday?
Yes,
Or do you have something else? How's the rest of your schedule looking? Do you have anything
We have
else?
a math test on Wednesday.
Okay.
Oh. No, I didn't manage it.
Math test on Wednesday. Okay. So Wednesday's out then. So either Tuesday or Thursday. What's the consensus? Okay, if you
can we have it on,
yeah?
can we have it on Thursday?
Okay, let's go. Who wants Tuesday? Put up your,
The girls at school on Tuesday.
the girls at school on Tuesday. Okay, so
Tuesday.
so those 3-4 votes. Who wants Tuesday? Daniela, what do you want?
Tuesday, please.
Tuesday. You see, we don't know what the other subjects are also giving you guys. Hey, so Tuesday. Who's totally set against Tuesday? You really can't do Tuesday. Uwami will be cool with Tuesday?
It's okay, ma'am.
Okay, thank you. All right, Tuesday. Okay, and it's going to be on everything we've done. Probably up until the end of page 5. Let's make it like that. Okay, the end of page 5 of your notes. So page 1 to 5, and that's going to be your test. I'm also going to make this for tomorrow. I'm going to make it count a little bit more than your other tasks, because I think it's a little more in depth as well. And then this can also see, you can also see now what to expect for your test. Okay. All right. So Tuesday next week, we can do that. All right. So
Ma'am?
Yes.
Will it also be on reactions in aqueous solutions?
It actually should be, because I have tested you a little bit. I've tested you on that. No, we haven't really tested you on that. No, you know what? Let's just make it physics. Okay. Let's just make it physics. What I can do with you next term, I can give you another little task on reaction rates before your exam. Okay, so let's just make it the physics. Let's make it page 1 to 5. And yeah. So have you guys got the declaration forms available? Has a teacher sent you declaration forms?
I don't think so, ma'am.
Okay. I'm going to get the declaration form. So what I need from you is you're going to have to make a declaration to say that when you sign and you send through your test, your completed test, you have to send through your declaration as well to say that you have completed the task without help and without looking at the computer or your phone or textbooks or notes. Okay. Another thing I'm going to have to ask you is, I'm going to give this to you soon. I need you to fill out an invigilation form. So somebody at home must sign, somebody over 21 must sign to say that they saw you and watched you finish the test in the time that I gave you, and you didn't have help. Okay, now remember, this is a legal document. Okay, so you must be honest with this. Okay, I'm not that I don't have any worries with any of you. I'm sure you guys are fine. Okay, so I'm going to send you 2 declaration forms, one for an invigilator to fill out, and I need that before your test on Tuesday. So I'm going to try and send it out today or tomorrow. And then number 2, I'm going to need a declaration from you saying that that's your own work and you didn't get any help, and that can come with the test. Okay. I will email it to you, or I'll email it to your parents maybe, because if they can maybe print it from home or something, and then you just take a photo of it like we normally do, okay? And I would imagine if your parents can print out a few of those, because there's going to be a lot of other tests and stuff that you're going to need that for other people's tests. I don't know if Matt has said anything. Has Mrs. Hopla said anything? I'm not sure. But you only need one teacher to send it to you, and then you've got it all the time. Okay. All right. So Tuesday. Okay. So what I want you to see here is, let's take a look at this. Now, it's not about the triangle with this. It's about the arrows. It's about the direction of the arrows. So if we had to say, oh, well, it's obvious, it must be the hypotenuse that's the resultant. It doesn't make sense, because if BC and AC were the vectors, that means that your resultant would land up over there in that way. So even though it could have the same magnitude, it doesn't have the right direction to be a resultant for this, okay? Because this one's going up and this one's going across. So your resultant would have to be there. So your AB is not the resultant of this. So let's see which one is. So remember I said to you, the one thing that could happen here is it could be a displacement. Now, it doesn't say anything. It just says a vector diagram. But if we follow here, if we go A, C, it's like we're walking. And then I go back and I go to B. Now, you can see here that this could then be the resultant. So imagine I'm walking here. Then I walk here. And I stop. Now, somebody wants to come and talk to you. They're just going to take the shortcut and go from there to there. And they land up in the same spot as you, but they didn't. It was a single vector that they used, where you used 2 vectors. Okay, so your resultant here is BC or CB, so it's C. So the key here was to look at the directions. All right, the next one. Now, I gave you a bit of a hint. Which one of you, okay, which one cannot be the resultant of the 2 forces? Who said A? Did anybody say A?
The girls at school.
Okay. B? C? D? No idea? Geez, you guys are talkative today. Okay. So I gave you this hint. Minimum resultant and maximum resultant. So for you to get a maximum resultant, so let's just read here. It says 2 forces of magnitudes, 11 newtons and 5 newtons respectively, act simultaneously on an object. So they act at the same time on an object. Which one of the following cannot be the resultant of the 2 forces? So let's consider the maximum resultant that it can be. So the maximum resultant is if they both act in the same direction, okay? Because that means that we would have to add them, okay? So that gives us a resultant of 16 newtons. So imagine you are pulling somebody and somebody's helping you pull that person, and the result is that you've now added. This is the maximum value that you can have, Okay. Now let's think about what would be the minimum. Well, if you're pulling something, the minimum would be if somebody's pulling in the direct opposite of you. So if this is 11 newtons and somebody is pulling in that direction 5 newtons, okay, that means that you're going to have to subtract them. So 11 minus 5 is 6. That's right, eh? So 6 newtons is the minimum value that you can have. Now, it does depend on the angles. So remember, you are going from there, where you are pulling in the same direction, and you can pull at any angle, your force can be pulled. But the minimum value is if you're going in the opposite. So any other angle would be between 6 and 16. Okay? If you pulled at an angle there, so say that was the 5 newtons, and this was the 11 newtons, you could work out a new resultant. Okay? You could work out a resultant, and we know that the max is 16 newtons, and the min would be 5 newtons. When you're adding 2 together in the same direction, that would be the very maximum. You can't get any more than the 2 acting in the same direction. And you can't get any less than the 2 acting in the opposite direction. So all your values have to be between 16 and 6. So the answer is A, because 5 is less than the minimum value. Okay? So, well done to the girls at school. Okay, I don't know if Gemma had a little hand in that. Okay, so 2 vectors, x and y, are shown in the following diagram. So this is the same thing. It says, for which of the diagram will the magnitude of the resultant x plus y be the minimum? So this is the same thing. If they're acting at angles, remember, if we're acting at angles, the resultant's still going to be in between those two. Okay? If they are acting in the same direction, it's going to be the maximum. If they are acting opposite, it's going to be the minimum. And if they're acting at angles to each other again, so it's going to be between minimum and maximum. So the answer here is C. So go CAC. Okay. Okay. So CAC, and there we have the answers. Any questions on these? No? Okay. Hope you all get that. Was there one? No. Okay. Right. So, frames of reference. Right. This has a lot to do with Newton's law of relativity. Okay, we never use the law. It's E equals MC. What's it? E equals MC squared. Gosh, I couldn't remember for a moment. Okay, you've all wanted to use that equation, I'm sure, but it's the famous equation. But we're not going to use it, but we're going to use the theory around it. Okay, so frames of reference. So what we are looking at, we are going, well, to understand a velocity or a vector, we need to be able to see things in different perspectives. Okay, so the train scenario is the best. So I'm just going to talk the train scenario through before we look at it on the note. So don't worry about the note yet. I'm not going to talk about that now. So I want you to imagine. So close your eyes where you are, and I want you to imagine that you are sitting on a train. Okay, you can see the world going by you, and you're sitting on the train. Now you're going to talk to your friend next to you. Okay, now because you're both on the moving train, that means that relative to you, you are still. Okay, you're not moving. Your friend is not moving relative to you. Okay, you both still. Somebody walks past you at 2 meters per second. they are moving 2 meters per second. Now, imagine you're coming to a station and you're passing a station and you can see a whole lot of people, okay? And now the people on the platform are looking at the train and they can see this person that's walked past you walking. Now imagine they're walking with the train in the direction of the train. Train is going to the right, this person's walking to the right. That person is going to be looks like, by relative to the people on the platform, as if they are going really fast, because they are on a train that is moving and they are moving on the train. Okay, so all right, let's come back to where we are now. So that is relativity. We are looking at relative to something, what is moving. Have you ever noticed a plane in the sky and it looks like the plane is just standing there? It doesn't look like it's moving at all. And you're like, oh my word, that plane is just sitting there in the middle of the sky. Meanwhile, relative to a bird in the sky, it is moving. But because you are moving in a car and the plane is so far away and also moving, relative to you, it could look like that plane has not moved. Okay. Have any of you been to the airport? Have you flown in an aeroplane? And when you go to the airport, you have those travelators. Actually, we can even talk about an escalator. Okay. Now imagine, okay, the travelators, that it's like moving floor, and you stand on it because the airports are so big that if you had to walk all that way, it's very tiresome. So there's these travelators. They're like horizontal escalators that you stand on it and you can just sit and well, stand and wait until you can get off again, and then it moves you. Okay. Now imagine, so you're on the travelator and you're moving, and then somebody walks next to you that's not on the travelator. Okay. If they're walking at the same speed as the travelator, it's going to look like they are still with you. Look, you know in your mind they're moving. Okay. But they're going to be next to you and not be moving faster or slower. They're moving with you. Okay. So relative to you, there's no velocity. Okay. Think about it. Then somebody on the travelator walks past you. They will have a velocity. Now imagine the person that's not on the travelator and sees that person walking. That person, or let's say that person is stationary now. So we are standing and we're watching the people walk by. Okay, we're watching the people. We can see the travelator and we can see the people on the travelator. So a person on the travelator that's just standing will look like they're going at the same speed as the travelator, and they'll go, let's say it's 2 meters per second, they're going to be going 2 meters per second past us. Then somebody on the travelator starts to walk faster, okay, on the travelator. Let's say they're going 3 meters per second on the travelator. So we're watching, they're going, oh my word, that guy's moving so fast. Because not only is he going 3 meters per second on the travelator, but the travelator is also taking him 2 meters per second. So relative to us, we see him going at 5 meters per second. Are you starting to understand what's going on here? Okay, it's all about relativity. Now, I want you to, when I talk about a frame of reference, I'm talking about a relative position, okay? Relative to this person, what does this do? Relative to this person, what does it look like? It's all about your perspective. How are you looking at it? Are you looking at it in the form of you're on the object? Are you looking at the object moving? Are you walking in one way and the object's moving in the other way? That's what we're looking at. So I want you to think about this as well. Imagine now, okay, let's go through the worksheet now. Let's go through. I think I'm done talking now without looking at the worksheet. Okay, so frames of reference. So speed, velocity, distance, displacement, etc. are all made relative to a frame of reference. Okay, So we can only talk about a velocity. So the cops that catch people with speeding, they are measuring the velocity relative to the ground, okay, or relative to themselves, all right? And how fast are you approaching them? And their little machine calculates that, okay, relative to themselves. If you had to look at relative to the moon, so you would put yourself on the moon and you're looking at the velocity of the car, it's not even going to register anything, okay? They're not going to be moving according to you on the moon, okay? So it's all about relativity. So Stacy is walking forward on a train. The train is moving forward, okay? The train is going at 10 meters per second, and Stacy is on the train, and she's also moving 2 meters per second, okay? How fast is Stacy walking? Relative, now this is the key, relative to a person on the train. So remember, you're on the train. Stacy walks past you at 2 meters per second, but you're on the train. What would Stacy look like she's doing? Anybody? She would look like she's doing 2 meters per second. Okay, you're on the train and she walks past you. You both have that 10 meters per second. Remember, your friend next to you looks like they're not moving according to you. Okay, if I had to say to you, you're sitting on a train and your friend is sitting next to you, what is the velocity of your friend? You can say 0, because relative to you, they're not moving. Relative to somebody at the platform, they're moving as fast as the train is moving. Okay, so relative to a person standing at the station as the train passes. So imagine you are now here. There you are at the station. Okay, a nice stick figure. Let's put some hair because you're looking at the train. Let's get you some little tufts. Oh gosh, I don't know what I'm doing now. Looks like a squashed bug. Okay, so let's take a look here now and we say, okay, yeah, you are sitting there and you see the train coming and it's going 10 meters per second. But Stacy is walking also in that direction and she's adding to the train's velocity. She's going fast. According to you, she would be traveling at 12 meters per second because she's walking on the moving train. Okay. If Stacy walked back to where she was at, I don't know why I said at 10 meters, how fast is Stacy walking? Oh, okay, I needed to say at 10 meters per second. Sorry, I left out the meters, the seconds, the per second. So Stacy's walking now backwards. Okay, so this is a very person on the stage. Imagine going 10 meters per second. That's 10 meters every second. It's quite fast. And I'm telling you that you're going to see something. You're really not going to see anything. But anyway, let's just pretend that we can. Okay, so if Stacy now, she changes direction and she walks backwards. So the train is going here and she's walking there. And she walks at 10 meters per second. Now she's running. Okay, so she is now running backwards at 10 meters per second. On a train that is taking her 10 meters per second to the right, she is now walking 10 seconds to the left. What is it going to look like Stacy's doing to the person on the station? They're going to just be stationary. So when you're on the train, she's going to look like she's going 10 meters per second in the opposite direction because you're also on the train. But relative to the person on the station, she's going to look like she's moving still because she's cancelling out the velocity of the train. It's like, you've all done this, when you see somebody and you're on an escalator and then you could see somebody in the opposite escalator and then you're going down and they're coming up and then you start walking up and they start walking down so you can have a little conversation and then together you're stationary. Meanwhile, the people are passing you all the time because you are, it keeps moving up, but you guys are now still, you are cancelling out the velocity of the escalator. And we've all done it where we try and run up the down escalator. We've all tried that, okay? And if you just walk at a constant, you are not going anywhere. You're cancelling out your velocities. You have to move at a faster velocity than the escalator to actually move up. Okay, so that's looking at that. So if she is on the train and it's moving to the right and she moves to the left at the same velocity to somebody outside, it's going to look like they're still. Even though you can see somebody moving, they are not going to, they're going to be directly in your line, and they're not going to look like they have moved left or right. Okay, so relative to the person on the train, she's moving 10 meters per second left. Okay, relative to a person standing at the station, it's going to look like she's going 0 meters per second. Okay, so to help you understand frames of reference, always put yourself in or on the frame of reference. So like I said to you, relative to a person standing on the platform, I want you to take, now this requires imagination. So you need to put yourself on the outside of the train at the platform, and you need to be looking at the train. If I say to you relative to a person on the train, you need to put yourself on the train and you can see the person walking. Okay, so an example, Superman is flying next to the plane, next to a plane, an aeroplane, which is flying at 950 kilometers per hour. According to a passenger on the flight, how fast is he flying? I wasn't clear yet. He's also moving at 950 kilometers per hour. So if he was next to the plane and looking at you and smiling and you waving back, looks like he is still. He doesn't have a velocity relative to you, okay? So he would be going 0 kilometers per hour, okay? Reference to the ground though, so somebody's looking up and going, oh, there's Superman. Wow, he's moving fast. He's moving at 950 kilometers per hour, which is the same speed as the plane that he's with. Okay, so that's what we're looking at. Okay, now the one thing I want to talk to you about is that it's not only velocity that we look at, it is also displacement. And that is what this exercise is about. So I'm going to look at it now quickly with you, and we're going to look at one and just see how we can do it. Okay. Any other questions regarding frames of reference? You guys are very quiet. I'm very worried. Remember, quiet means that you all understand to a teacher. So please.
Ma'am, we're just taking extra time to process.
Sorry, say that again.
We're just taking extra time to process.
Okay, that's fine. I really hate that I can't. You really should show me your faces, because I'm battling to connect with you to see if you're okay. So if you're nodding, I can see, okay, you're getting it. If you're going, what? And you're pulling a face, I can go, okay, let me rephrase that. So it's very difficult. So you need to tell me. Do you want another questionnaire? Did I give you a questionnaire already? I can give you a questionnaire again, and you can see if you're happy. What page are we on? Page 269. Okay, page 269. I'm quickly going to do one with you so that I can do any things with you. Any problems for tomorrow's task with you. So we've still got about 15 minutes. Can you see that? I can't see. Let me see what you're seeing. Yes. Okay. So this is now looking at frame of reference. So it says frame of reference is described below. Oh, I hate it when they do this. I really wish they had to put this on the next page, because now the questions are on the next page. Oh, frustrates me. Okay, so let's just take a look here. They've got, it's like a number line, and they're saying there's A, B, C, D, and then they're saying this is 0 over there. So if we go to the next page, and it says a positive direction represents forward motion. Okay, so all the positives are forward, and the negatives are reversed. So describe the position of. So this is all, I want you to just do this one with me. Okay, I'm actually going to redraw this because I want to talk it through. So if you want to do that, you can do it. So we go -3, -2, -1, 0, 1, 2, and 3. Okay, we have DC. There's a triangle there, and then we have AB. Okay, can you see what I've done? Okay, that's what I've done there. So I've put the reference diagram there. So I just want you to do this. So let's say relative to the A relative to origin. So you're going to look at this, and I think, let me just see. It doesn't say if it's in meters, so let's just say it's meters. Okay. So we're going to describe the position of A relative to the origin. So here's A, here's the origin. How can we say where A is relative to the origin? The numbers are representing meters. So if I was to say this to you, I would describe A is 2 meters to the right of the origin. Would you agree with that? Okay, so this is also a frame of reference. So if I just said to you, where is A? You're just going to go 2. You know, like, but you need to describe if it's a change in your position or if it's a displacement, you need to give me more information. I need to know. I can't just say, where is the nearest McDonald's? And you go 5. That means nothing. If you'd go 5 meters left and 2 meters right or whatever, then I know. I'm like, oh, okay, from where I am, it's 5 meters to the left. Okay, so you have to have the frame of reference. So I've spoken about velocity, and now I want you to look at displacement. Just one question first. I want you to think about this carefully. And I want an answer. You can WhatsApp it later if you want, or if you want to give it to me now, you can. 2 cars, okay? One is going 5 meters per second. The other one is going 4 meters per second. They collide head on, okay? They collide head on. How fast did the 4 meter per second car look like it was going to the 4 meter per second one? Is that right? So let's say A was 4 meters per second, B 5 meters per second. Doesn't matter. Okay? They are heading towards each other. Okay? Imagine you are sitting in A. Okay, you're not going to collide. You're going to stop before them. Okay, but you see a car coming towards you, right? A is 4 meters per second. B is 5 meters per second. You are sitting in A. How fast does B look like it's going? Okay, that's the question. I want you to think about it. Okay, so I want you to do 1.1 to 1.10. And that's all I want you to do. So you can start that. Any questions regarding tomorrow's task?
No, ma'am.
Ma'am, what all will it be on?
Okay, it's going to be on your trigonometry. So make sure your trig stuff's with you tomorrow. It's going to be on, I'm going to ask you to calculate a resultant force, where I give you 2 forces. I'm going to ask you to calculate the direction of the resultant. I'm also going to give you a resultant and ask you to get the x component and the y component. Okay, so everything that we've done with vectors, I want you to be tested on now. Okay.
Okay, ma'am.
Then next week, because then we can deal with any problems that we have with it, so that next week when I give you your test, you are cool.
And ma'am, for this activity, on page 270, it says The positive direction represents forward motion. So would A be in front of the origin then?
Yeah, I suppose. Let's say that positive is to the right. I don't like that it says forward motion. I want a proper direction. So let's say positive is to the right, negative is to the left. I prefer you to pick an actual direction. Okay. So yeah, let's do that. Positive is right, negative is left.
Thanks, ma'am.
Rose, what was
Okay, continue with that. And you can ask me questions as we go. Okay, girls, we'll call it for today. Get ready for your next class. Okay. And I will post the task before your lesson tomorrow so that you can start immediately. Okay.
Bye, ma'am.
Bye.
Ma'am,
Yeah.
for the car scenario, would it be 9 meters per second?
I see.
Yes. Good.
Cool.
Yeah. Because
Bye, ma'am.
you're moving and they're moving. And so you're adding your two velocities even though you're moving in the opposite direction.
Bye, ma'am.
Cool. All right. Bye.